Okay, here we've got our stress analysis with Inventor assignment. Let's open that up and see what we've got. So with Inventor, you can actually calculate the amount of stress and strain inside of a part. So basically, how far is it going to move by being forced, and how much stress, like how much pressure is inside the material. So like, for example, did you build the stoplight strong enough to withstand the wind? Kind of important for an engineer to know how to do. So anyway, so you can read this stuff. I tried to explain finite element analysis as best and concisely as I could. And we're going to test to see if that works and check it with a hand calculation. So here, just as a simple situation, common engineering situation, you've got a cantilevered beam supported at one end and a load at the other end. In this case, it's a rectangular cross-section. I've already looked up the equations for you and the material properties that you need. So let's go ahead and calculate how far this beam should deflect. So basically, how far is this point going to actually move downwards because of that force? So let's go ahead and do the calculation. It says the deflection is FL cubed over 3EI. All right, so I'll walk you through that. So we've got 50 pounds force times we've got 10 inches. That's the length cubed. Okay, then we're going to divide by 3 times the modulus of elasticity. That's basically how many pounds of stretching that material would cause it to stretch like 1 inch. It's kind of like the stiffness, like the spring constant of the material. I believe in this case it is 29 million. Let's just check here. Yeah, 29 million psi. Okay, so we're just going to go ahead and type that in. So 29 times 10 to the 6 pounds per square inch. Okay, then we've got to also multiply in that denominator by the area moment of inertia, I, which is just a handy geometric quantity. Helps us with these calculations here. So I believe it is, shoot, I already forgot. It's base times height cubed over 12. All right, so base times height cubed. So that would be 0.5 inches times the height cubed, 0.375. I'm going to put that in parentheses, 0.375 inches cubed, and then all over 12, right? Okay, I'm going to crunch some numbers and I'll be right back. Alright, so when I crunch the numbers, I got 2.6 times 10 to the negative 4th inches. So basically, 3/10,000ths of an inch. We would expect this thing to actually deflect downwards. Okay, so let's go ahead and do the same thing with the stress. So the stress, that's like how much pressure is inside the material. Materials can only take a certain amount of pressure before they break or before they become permanently deformed. So it's an important thing to check. So again, we've got 50 pounds, and then we times our length, which was 10 inches, and then divided by the section modulus, just another handy geometric quantity. So it's base times height, so it's let's put this in parentheses, 0.5 inches times the height squared, 0.375 inches squared, and then divided by 6. Okay, I'll crunch that and be right with you. Alright, so what I got was 42,666 pounds per square inch. So you see how the units work? You've got pounds in the numerator, and then you've got inches cubed in the denominator, but inches in the numerator, so in the end you get square inches in the denominator. Okay, so the next thing we're going to do is we're going to model this in Inventor and see if this actually checks out. So I'm just going to go ahead, model this up in Inventor. I've already got Inventor open. Let me pause it. Alright, so I've started a new part. Going to make a new sketch. And it's pretty easy. Let's just do a rectangle with dimensions of 1/2 inch wide 0.375 inches tall. And let's go ahead and extrude it. 10 inches. Very good. Now we've got our beam. Okay, next thing you want to do is click on environments and then stress analysis. Okay, first thing we're going to do, create simulation. This is, make sure you have static analysis selected. I think everything else is okay. Okay, next thing we're going to do is assign the material. We're going to click on materials and we're going to find steel. Double click on it. Should be right. Let's just make sure it says steel. Okay, now we have to tell it where is this part held, otherwise it would just be floating through space. So we're going to hold it here, maybe at this end. And then we're going to apply a force at the other end, right on that edge there. And the direction we're going to say is right up and down. For some reason I want it to point that way. And then it was 50 pounds. We're going to say OK. And then we're going to click Simulate and click Run. Alright, so as we can see, the simulation has finished. It's really cool. You can see a visual of like where the highest stresses are. So you could imagine probably right here, right where it's held to the wall. That's going to be like where it would break, right? All right, so let's check the von Mises stress. Von Mises stress is, where is the maximum stress? Well, looks like 42,000 psi, which is right around where we calculated. Now let's check the displacement. Double click on it. This is saying 0.2, so this is saying a 1/4 inch. Let me recheck my calculation for the displacement. I'll be right back. I did find a mistake on my calculator. I will show you. So if you can see up there, see where I said 29E9, but it was actually 29 million. See right there. It was actually 29 million, right? 29 million pounds per square inch. So I was off by a factor of 1,000. I'm dividing by 1,000 times too much. So the answer really should have been 1,000 times less, so 0.26. This is saying 0.25. So the simulation is different by 1/100 of an inch. You know, it's not a perfect simulation. The equation's not perfect either. You know, real life is real life. If you read about the finite element analysis, you'll see that, you know, it's really approximating this beam into several springs. And actually, maybe we could see that if you click on Mesh View. So each one of these is kind of like its own spring, you know, and we know how to calculate springs. Sometimes we don't know how to calculate complex geometry, you know, like this, for example. You know, so you have to break it up into several different springs. So anyway, so that's how you do that. If you could just include a screenshot of your finite element solution and your hand calculations, then you'll be done.